Okay, so hi everybody. So this is 5.5 and it's the very last of 5.5. And basically, we're still dealing with the substitution rule, but now we're gonna see how the substitution rule affects definite integrals. So recall that indefinite integrals are integrals that do not have bounds here, a and b. So they're just general integrals. And if we take the antiderivative, we need to add a plus c. But for definite integrals, we have the bounds a and b, which tells us that we're going to find the area of the function that's inside between a and b. And we evaluate them at those points. Now, in reality, the substitution rule for definite integrals and indefinite integrals is exactly the same. The only thing is that when you're dealing with a definite integral, you have to account for your bounds. And so you have to adjust your bounds based on what you let u equal. So the substitution rule for definite integral says that if g prime is continuous on AB, and if f is continuous on the range of u, which is equal to g of x, that's the function that we let equal g of x, then our substitution rule is still going to be the same, but now we're going to plug in the values for a and b into our g of x, which is normally u. Okay, so there's two ways to actually adjust for those bounds. And so I'll show you both methods. So let's say we have the integral from 1 to 2 of 1 over 3 minus 5 all squared dx. Now, so far, right now, all we want to do is evaluate this. Like, we can't actually take the antiderivative of this inside function right now as is. So we know that we're going to need to do u substitution. But so when we do our u substitution, we normally let u be our inside. So we're going to let u equal 3 minus 5x. So far, everything is as normal. And we're still going to calculate the derivative of u, which is going to be negative 5 dx. And I go and I look back at my integral and I don't see a negative 5 in here anywhere. So I'm going to go ahead and divide that out. So I'm going to get 1 over 5, and that was negative, du is equal to dx. So now I'm going to rewrite my integral in terms of u. And now I'm going to get 1 over u squared du. Now I was able to replace it, but now what we need to do is we need to account for what's going to go in these spots now. Because when we were doing the integral from 1 to 2, we had the variable x, and it was for the variable x. Now we have a different variable u, so our new bounds have to be for u. So how do we do this? So the way we're going to do this is we're going to consider what we let u equal and then what x is at that spot. So the definition says that we're going to let u equal g of x, and we're going to evaluate g of b and g of a. So that's exactly what we're going to do. We're going to evaluate those bounds. So when our a value, so remember this is a to b. When a was equal to 1, right, this was our x value that was equal to 1. So what we're going to do is now we're going to say then u equals 3 minus 5 times 1. And that's how we're going to get our new lower bound. And so when we do that, we'll get negative 2. And so that means that our new lower bound is going to be negative 2. So what happened was I'm going to use the old lower bound a, and I'm going to plug it in for u to figure out that new lower bound over here. And I'm going to do the same thing with the top one. So I'm going to say when x was equal to 2, in this case, which is equal to b, our upper bound, we are going to say that u is going to equal 3 minus 5 times 2. So your new bounds depend on the function that you let u equal, so that inner function. And then here we're going to just get u is equal to negative 7. And so that means inside our little box here, we're going to get negative 7. And now we can integrate. So when we integrate, we're going to get, I'm going to rewrite this integral nicer. It's going to be the integral from negative 2 to negative 7 of u to the negative 2 du. And now we can just simply do that backwards power rule that we know how to do already, hopefully. And so when we do that backwards power rule, we'll get negative 1 over 5 because it was on the outside. I'm going to add 1 to the exponent, which makes it negative 1, and then I divide by a negative 1. So it's going to be u to the negative 1, evaluated from negative 2 to negative 7. Okay, perfect. And now I'm just going to rewrite this so it's not in the, I don't have any negative exponents, so I could evaluate it a little bit better. This is going to be 1 over u, and they're both negative, from negative 2 to negative 7. Okay, and now it's our job to evaluate the upper bounds by doing f of b minus f of a, so doing that fundamental theorem of calculus. So when we do that fundamental theorem of calculus, we are still going to have negative 5 in the front. Then we're going to do f of b, which is negative 1 over negative 7, minus f of a, which is negative 1 over negative 2. Now we're going to evaluate this. So here we're going to the value here positive minus a negative, so we're going to get negative 1 over 5 times 1 over 7 minus 1 over 2. Okay, and if we simplify this, we'll simply just get a 1 over 14 value. Okay, but as I mentioned, there is 2 ways to do this. So one way is to adjust your upper and lower bounds from the start as soon as you let u equal that inside function that you want. The second step allows you to avoid doing those upper bounds, but you have to be really careful with the notation. So I'm going to show you exactly how to do it. So there's 2 ways to do it. And so maybe practice both ways and see which way you like better. But regardless of the way that you choose, you have to remember to adjust your upper bounds, because if you don't adjust your upper bounds, that you're not actually getting the area of the function at all between those 2 bounds. So I'll show you how to do that in just 1 second. Okay, so the other way to do it is to wait to evaluate So another way to do this is to wait to evaluate until you integrate with respect to u and then switch the u function for the x function. You need to be really careful when you do this, because I will mark points off if you rewrite what I'm about to show you. So same problem, but I just want to show you how it works. Is we still pick our u to be 3 minus 5x. Everything is the same. But when you plug u back into that integral, when you get negative 1/5 u to the negative 2 du, right? I'm just plugging that back in. When you switch it back in, you cannot rewrite 1 and 2. This is wrong, because once you switch to u, your bounds are no longer 1 and 2. At all. If I catch you writing 1 and 2, I will take a lot of points off for you writing 1 and 2 if you have switched the bounds and didn't adjust correctly. The best advice is that you just put a question mark, is that you switch to u, but instead just put a question mark like, hey, I didn't calculate u, I didn't adjust them. That's fine. You don't need to adjust them. And then what you want to do here is integrate like you normally would. So remember that when we integrated, we got negative 5, negative 1 over u. And now instead of writing our bounds, we'll still write our bounds like this. Because like I said, you didn't go ahead and calculate them. So this is just another way to do it. But now what you're going to do is you're going to switch to x and go, okay, this is the same thing as negative 1 over 5, negative 1 over 3 minus 5x. And the moment that you switch back to that x value, you could come back to your bounds over here. But it could only be once you've switched back. So you have 2 options. Adjust u from the start so that you get the correct bounds, or get your u's, leave these blank or put question marks here. Go back to x and then evaluate these for x. So when we go back to x, and I'll show you, you'll get the exact same thing. When we evaluate this, we're going to get negative 1 over 5 times f of b minus f of a, which is negative 1 over 3 minus 5 times 2 minus 1 over 3 minus 5 times 1, which is the same thing as negative 1 over 5 times 1 over 7 minus 1 over 2, which is exactly what we got last time. So pick your preference. You should know how to do both and understand how to do both. Okay, just because, moving on. But like if your friend does it this way and you do it this way, they're the exact same way. It's just, you should know that even if you decide to, just stay and do it this way because you don't want to adjust the u, that's fine. You can keep it like this, but keep it in the back of your mind that when you do this, your u bounds are different than your x bounds. Okay, so that's basically it. I'm just going to do one example so that you can see how it works, because most of it is just, adjust your u. So I'll actually have you try, and I'll just give you the answer for this. And good idea is to do it both ways by adjusting u, and then the other way by doing it by waiting until the end to sub for x and then doing it. Okay, so I want you to evaluate this integral, and the answer to this is 81. Okay, and now what we're going to do is, so go ahead and try this yourself and make sure that you get 81. So try it using the obviously you need to use u substitution, but 1, try it using adjusting your bounds from the start, and then 2, maybe try it till waiting to the end when you sub back in for x. Okay, and then the last thing we're going to talk about in this section is integrals of symmetric functions. And so we've talked about symmetric functions before, remember that we have even, odd, periodic functions. And so the good thing is that there's a really nice thing that happens that when you're integrating from negative a to a, so let's say you were integrating between negative 1 and 1, if your function is even, then all you have to do is go from 0 to a and multiply times 2. So this is what the integral of symmetric function is saying. So suppose you have a function f and it's continuous on negative a to a. So your goal is going to be to evaluate that integral between negative a and a. And it's saying if f is even, which means that f of x is equal to, f of negative x is equal to f of x, then instead of integrating from negative a to a, f of x dx, you can integrate 2 times 0 to a. And why would you want to do that? Well, a lot of the times when you have an integral, a value of 0, it actually makes your life a lot easier because you're doing f of b minus f of a. And if one of those bounds is 0, sometimes, that f of b or the f of a will 0 out. Not all the time, but it just makes your calculations a lot easier to do. And so why does this work? Well, if you have an even function, right, you have some function that looks, I don't know, like this. And we'll do an example of this. And let's say you're going from negative a to a. Well, if you want to know the area between these curves, if it's even, that means it's symmetric across the y-axis. All they have to do is calculate an area, the left-hand side area or the right-hand side area, and multiply it by 2 because I have 2 of these areas. That's all that one's saying. The next one is saying that if you have an odd function, which means that when you do f of negative x and that equals negative f of x, then when you do the integral from negative a to a, then you're actually going to get 0. If you do ever use these properties in your homework or on an exam, then I'm going to need you to say why you can do it. Okay, you can't just do it and tell me that the area is 0. Okay, so why does this work? So let's say you have, let's do the cubic function, right? The cubic function looks like this. Wow, that was horrible. But let's say we were doing the area from negative a to a. Now that means that you're trying to calculate this area and this. But this area is exactly the same as this area, except for this area is negative and this one's positive. And if you add two of the same numbers together and one is negative and one is positive, then you're going to get 0. That's all that's saying. So if you have an odd function that you know for sure is odd and you're going from negative a to a, then the answer is just 0 because it's odd. So let's do a few examples. So let's say we have the integral from negative 3 to 3. And let's do a very famous even function, which is just a parabola, just so that you can see how this works. And so you're able to do this nicely. So let's say we want to find the area between negative 3 to 3. So we know that this function is even. So the way that you'll write this is since f of x is equal, since negative f of x, you'll write since f of negative x is equal to f of x, then the integral from negative 3 to 3 of x squared dx is the same thing as the integral from 0 to 3 x squared dx multiplied by 2. So all I'm going to do is I'm going to get this area on this side, and I'm going to multiply this area by 2 because then that's going to give me this side as well. And the way that you check for even and odd functions is, remember, all you do is you plug in f of negative x. F of negative x is the same thing as negative x all squared, which is x squared, which is equal to f of x. So this is what this part here is saying. And now we can easily integrate this function, right? So we had 2 times x squared dx. We just apply that backwards power rule, and we'll get x cubed over 3 evaluated from 0 to 3. Okay, and so now from here, all you're going to do is just do your f of b minus f of a, which is going to be 3 cubed over 3 minus 0 cubed over 0. And so the reason it's nice to use these properties of symmetric functions when evaluating integrals with the same bound, just different signs, is that you get this nice going on here. So instead of doing negative 3 to 3, yeah, we probably, negative 3 to 3, we wouldn't have to do 3 cubed over 3 minus negative 3 cubed over, minus negative 3 cubed over 3. Oh, this should be a 3, sorry. Look like a 0. Yeah. So it just makes your life a little bit easier because this side goes to 0. Now, it doesn't always go to 0, but it does make things a lot nicer. And now if we evaluate this, we'll just get 2 over 9, which is equal to 18. And so that's the area between both of these curves. Okay? So very nice property. And so now let's do one for the odd functions so that you can see. So let's say you were integrating the negative pi to pi of sine x. Now sine x is an odd function. If you recall, sine x looks like this. Oh wow. Sine x looks like that. And then like this, you know, and it just keeps going over and over and over again. So when we're trying to do this area between pi and pi, we're trying to calculate this area and this area here. Now, sine is an odd function because if you do sine of negative x, you'll get negative sine of x. And that's a property you should have learned in your 125. So you should know which trig functions are even and odd. Your cosine function is even, your sine function is odd, and it's because it's symmetric around the origin. So the symmetry happens here. Okay, so now what you want to do is, all you're going to say is, since f negative x is equal to negative f of x, which this really means that sine of negative x is equal to negative sine of x. So sine of negative x, so sine of negative x is equal to negative sine of x. So it's saying that since this is true, then the integral from negative pi to pi of sine x is equal to 0, and you're done. So this tells me that it's odd. So instead of writing this statement too, you can write, since sine of x is odd, then this is, I need to know why you're saying that it's 0. Don't just tell me it's 0 because you think it's an odd function. You should know that it is an odd function, or it's not an odd function, or it's an even function. And how do you show that? Now for your sine and cosine, I'm okay with you knowing that it's just odd and even. You should have been able to learn those in your 125 class. So just keep that in mind. And yeah, and that's it for 5. And then we'll just do 7.1, and that'll be the end of Calculus 1.